Pytorch is one of the most powerful tools available for doing serious machine learning work, used both in industry and in academic research alike. Join me today as we learn the core features of this tool and begin our journey into deep neural networks. Hi, my name is Gregory Topline with GNT Learning. On this episode, I'm going to help you understand how to do a basic Pytorch setup. To that end, we're going to prepare data, define a model architecture, train that model architecture, and then evaluate our results. Our overall goal today is to build up the code boilerplate we need in order to access the core functionality of Pytorch, and along the way spend some time understanding and debugging the most common errors that occur. Now, going into this, we're going to assume you have a basic understanding of gradient descent, backpropagation, and the various underpinnings of machine learning. Our focus today is instead to move past theory and into production of actual code. We're going to start off today by bringing in our standard set of imports into Python. Next, we need some data to work with. Now, our goal today is to create a minimal viable Pytorch model. So we want a data set that's already clean, contains nothing but numeric values, and is a natural choice for target variable. The data set that's going to work well for us is this Pima Indians diabetes data set that's available from Kaggle, among other places. This data set describes a number of different health indicators and whether or not the individual had diabetes, as defined by this outcome here. Now, in general, Kaggle has a nice little description, summary of histograms of everything that's going on here, but it's good practice that even though I generally trust Kaggle, to look at the data a little bit more. So we're going to investigate what's going on here with df.info, take a glance, and we can go ahead and see that we do have no missing values at all. Everything has the same number of non-null values, everything is numeric type, and at a glance things seem pretty reasonable. However, there's a few things to note. So if we look at the data itself, we do see there's a lot of zero values here for insulin and skin thickness as well. Now, it can be when you have data that the NAs have been replaced by a 0 or some other filled value. And so you should be a little suspicious when you see a lot of zeros for com. Is this a reasonable value or is this some sort of NA fill? To get a better idea, we're going to go ahead and create some histograms to see what's going on. So first, let's look at the skin thickness histogram. Run that. All right. And at a glance, it seems like a reasonable looking histogram, right? There's some values, they're spread out, okay. But if we take a moment to think about it, we're seeing there is a bigger peak at the front end here. And what we're really worried about is not that there's more values at the low or high end. We're interested in seeing there's a really sharply peaked answer at a value of 0. So to help us see that a little more clearly, we're going to set the number of bins equal to 50 and run this again. Now we can see pretty clearly that there's a Gaussian-like distribution of amount of or skin thickness values, but there's this really strong peak at 0. All right, so first question is this a problem with the data set? Well, after a little bit of research, you find out that skin thickness test is one where they just try to see there's loose skin, and if so, how thick the piece of skin you pull away is. In this case, it would be very reasonable for someone to have tight skin, and hence there not to be any value for skin thickness. So 0 is actually a very reasonable value here, even though it does kind of break the normal Gaussian distribution. That said, it's not actually going to be a problem for us. However, if you're building a model with something like this, depending on the type of model you're using, it may or may not handle this very well. Something like a logistic regression, for example, will try to put a connection between the amount here and an outcome. That sort of continuous approach is not going to behave especially well with all these zeros, although it can work. What's going to perhaps do a little bit better is a neural network where you can make a decision and say, okay, if it's a value below 0.0001, i.e. value of 0, then do one thing with the data, and if it's above that, then do something else. And that ability to have this sort of stepwise decision-making allows neural networks to perform better in some applications. So this is actually a data set that's going to be more attuned to being worked on with a neural network. Now, over here, we should do a little more analysis for completeness and go ahead and look at the insulin case as well. So here, we're going to do insulin and set the bins equal to 50 yet again. And when we run this, we get basically the same kind of result. Now here, the result is a little bit less Gaussian, but that's not necessarily a problem. And again, a neural network should have some ability, some resiliency to figure out what's going on with this. And in the case of insulin, again, it is very reasonable that you may not be taking insulin, so the value of 0 kind of makes sense with what's going on. It's not just a random NA fill. So we're pretty happy with these two values. So we don't really need to do anything here. We can just proceed with the data as is and continue with the model. So given that we could have just ignored this problem completely, why did we stop at having a side to examine this data and look at these histograms? And the reason for it is there's a really important issue that comes up with Pytorch or really any other tool. When you start digging into some more complicated tool to do machine learning, a lot of times the first problems you're going to run into are nothing to do with the tool itself and everything to do with the data. It is always worth your time to look at the data a little bit more rather than barreling ahead, because it can be that there is a mistake or is a problem and that you'll get completely caught up in the new tool, trying to figure it out, trying to debug it, when you could be doing it completely correctly and the problem is with the data. So do yourself a favor, take some time, inspect that thing that looks a little bit suspicious. Now that we have the data we want, let's go ahead and pull it out of the data frame and put it into some variables so we can actually begin working on it. All right. So here I'm just going to do this by the index of the columns themselves. In our case, the first n columns were all our features, and our final column, -1, was the actual outcome we're interested in fitting. Now, it's not really necessary here to do .value, but I find it to be a useful practice that if you know you just want the underlying raw numpy values, just put .value so you clear for yourself. Again, not technically important here. Okay, go ahead and run that and realize that I made a typo. Need values. All right. Now, for any decent model, we're going to want to do a test train split and normalize the data as well. Now, for today's purposes, I'm not going to get into a detailed discussion of these topics. We're just going to go ahead and implement a standard scaling and test train split. To do that, we're going to have to pull in two imports. So from sklearn.model selection, we want to import train test split, and from sklearn dot pre-processing, we're going to import a min-max scaler. All right, scaler, and as always, make sure to run your cell. Coming on down, we can then use what's going to be very much a standard boilerplate code to do our test train split. Test y train y test is going to equal train test split xy, and here we're just going to set a test size of 10%. There's no particular rhyme or reason for that. In this case, it's just a reasonable value to put in. We're not going to overthink the exact details of this in this video. Now, once we have the test train split done, we can go ahead and do the scaling. We're going to use a min-max scaler today, which is a more sensible choice when you have some naturally bounded values. For example, there's a minimum number of pregnancies of 0, a minimum insulin input of 0. And because you have these sort of bounded values, it makes a little more sense just to use min-max scaler across the board. And then to actually implement the scaling, we have to fit and transform the data on the training set, but then we only want to transform the test set because the actual values for the min and max are learned from the training set. And as always, try to catch your typos if you can. So at this point, we've done our standard data loading that would be true of any model or any framework we're going to use. Now we want to go and move into doing Pytorch. So first, we're just going to go ahead and import Torch itself. We're going to have some more specific imports in a little bit. Ran that. Now, what makes Pytorch Pytorch? Well, under the hood, Pytorch tracks how values are actually calculated. Whereas in NumPy, if I write something like a equals b plus c, you could have b and c be some NumPy arrays, and you can do the math, you can get what a is. That's fine. In Pytorch, though, we go a little bit further. A remembers that b and c were used to calculate it, which means that you can do something a little more complicated, like say, what is the derivative of a with respect to b, and Pytorch can figure it out for you. And this is what enables backpropagation to be automated and allow the heavy lifting in machine learning calculations to be done for us. So Pytorch and other frameworks rely on these graphs of connections to understand how the variables are interconnected and do all the heavy lifting we need. To take advantage of that, we need to convert our inputs, in this case the training and test values, into torch tensor objects. To do that, we can very simply go ahead and just call torch.tensor on a NumPy object, and it will create a torch tensor object with the same initial values. All right, and we're going to go ahead and do this again for our testing and training data and our x and y values. Now, one caveat here is you'll notice that I'm reusing variable names. I'm using xtest here, and as well as previously in the cell above where I calculated initially. And in the first case, it's a NumPy object, and after this case, it's a torch tensor object. In general, you don't want to be mixing up types like this. You want to have each variable have a clear identity of what kind of thing it is, and have that not change. In this case, I'm just viewing the xtest and xtrain values that came out of this previous cell as temporary NumPy arrays that are immediately going to be torch tensor objects. So I know they're going to be torch tensor objects for the rest of this code. So I don't mind just reusing the variable here. So we go ahead and define our torch tensor objects. All right. And next we need to look at how we actually want to load data into the model itself. Now we have it in a torch tensor. And to do this, we're going to need to go and bring in two more imports here. So from torch.utils.data, we're going to import tensor dataset and data loader. Now these two pieces here are really the standard way of channeling data into a model for Pytorch. All right, we can go ahead and come back down. The first of those was the data set. And what we're going to use this data set for is to go ahead and glue together the X and Y data that we have for training and test into two separate data set objects, a train data set and a test data set. Now let's go ahead and just do one of these for a moment. Now, at a glance, this doesn't look like the most meaningful piece of code. So what it's really doing is it's just saying, oh, okay, if I want to grab the fourth item from my training set, I can go ahead and grab it like this. And this is literally identical, in this case, to doing the same thing a little bit more directly on the X and Y train themselves. Right? So this doesn't really look like anything. The reason this dataset idea is powerful, though, is you're not always taking data from a NumPy array that you loaded in from some CSV file. If you're doing a more complicated input, for example, loading images that are just too big to load them all into memory at the same time, what Pytorch provides is different types of datasets besides tensor datasets that allow you to automate the loading of these things in a programmatic way that continuously pulls them in from memory. And it does this while presenting an interface that looks just like this. So even if under the hood something much more complicated has to happen, when you want to access the data, you can just grab it directly like this. And again, in the case of a tensor object, it doesn't really look like it does a whole lot for us, but it's a good idea to stick to this usual formalism and use these data sets in Pytorch. If you're doing something particularly complicated, you can build your own custom data set that can load in data in whatever way, shape, or form is needed, and again, provides the same kind of interface. Generally speaking, though, there will be a data set that exists in Pytorch for your exact need, whether it's loading images or some other common input type. Now, we have our training data set, and as you might imagine, the creation of a test data set is not meaningfully different. So go ahead and get that in here. Test and test. Right. And the second thing we're going to do here, besides clean up our little demonstration, is go ahead and use a data loader. Now, a data loader is a wrapper for the data set we just created. So data loader, train data set. Now, what this does is it says, okay, it's wonderful using the data set to get a value, but usually when we're doing an actual machine learning project, we're not doing values one at a time. We're doing more complicated things. At a minimum, we're usually using a batch of data. So here we can set the batch size. You can also use other features in the data loader for more complicated things. For example, you can augment data. You can, by having different versions of it produced from the raw input. You can also do things like shuffle the data, etc., etc. So there's a lot of other options available here. Today, we only really need the batch set size set to 32. And it is important to use the right variable name there. All right, so you go ahead and do that. And we created our data loader objects. And these data loaders are what we're going to loop through and provide a useful interface for us. All right. So now that we have the data in this nice little pre-packaged tool we can use, we need to actually define our model. To do that, we need to define a custom class. Now, for those with a non-CS background, class is just a way to bundle together a lot of data and or methods in one place in a well-defined object. In this case, we have a class that's going to define what a model is for us. In the same way that sklearn, for example, creates a class that represents a logistic regression or a decision tree, we're going to create a class that represents the model we're building. To do that, we're first going to write the most generic possible class we can, and then we'll work on customizing it for our specific application. All right. So in this case, the class we need to build has to import from this torch nn.module. And this module really just says this is a thing that can be used as a model. And we only have to define two methods ourselves. One of them is going to be the init. And in that init, we can define whatever data we need to create that's going to be part of the persistent model. And then we can go ahead and call the init on the super to instantiate the other pieces that we're getting for free from our inheritance. And then we can go ahead and define a forward method that goes and takes whatever things we've defined and tells how we're going to do the math and glue those pieces together. All right. Now this technically here is a valid Pytorch model. It is, of course, the dumbest possible model because all it actually does is it takes some input and then returns it exactly as it was unchanged. So not really a valid one to use, but is a good place for just the minimal boilerplate, especially for those that are less familiar with classes and programming and need just a minimal thing to see. So we're just going to go ahead and leave this here and have it commented out for reference. And what we're going to do instead is build our own little model, and we're going to make a one hidden layer neural network. So let's start off by giving our model a intelligent sounding name. How about NN1 hidden? And actually I want to go ahead and put this after this. All right, so we're going to have two layers in our one hidden layer neural network. The first layer is going to be what is called a linear layer in Pytorch, called dense layer in some other places, or a fully connected layer, depending on what your background is. And this layer is going to take an input with some number of features and then create an output that has some hidden number of nodes, in this case is our hidden dimension. Then we have a second layer that's going to do essentially the same thing. And in this case, the size is going to match the output of the previous layer. And then our output of this is going to be 1 because we're making a binary decision about whether or not someone has diabetes. Now, a little bit of syntax details here. Now, the self is just part of the syntax for a class, and it basically says that this fc1 variable is part of and attached to this class. Second, this torch.nn is part of a broader set of things defined within Pytorch. There's a lot of very standard layers where there are dense, fully connected layers, or convolutional layers, or pools, or whatever you want. Those things are all very common little pieces that are defined in different variables, or different classes rather, within Pytorch. In this case, we're just using two very simple, fully connected layers, one after the other. Now, technically, in the init, all we're defining is what the pieces we're using are. There's no code here that's actually in any way saying that this one's first and this one's second, other than perhaps our naming convention. And that's what the forward does. The forward says, okay, given these different objects you've created that you want to use for the model, how do we actually glue them together? So we're going to say, take the fc1 of x, so take our input, push it through this layer. Next, we then want to do an activation function, in this case relu, and these activation functions are part of another import, which we need to go ahead and scroll back up and add. Let's go ahead and do that real fast so we don't forget. And these activation functions within Pytorch are part of a larger set of functionals, as they're called, or functional pieces, as they're called, that allow us to do various operations, softmax, relu, for example, but there's a lot of other little math like sine, cosine, things available within functional. So you can do whatever little math is necessary, and helps to spell variables correctly. All right, so you have functional math. So coming back down, we can just say f.relu, so we can just want the relu function, apply it to our x, and then we can go ahead and push our model through the second layer, fc2. Finally, then we can return the value. So in this way, we've defined a model. Now, a few takeaways here are: one, in the init, we define what pieces are going to go into our model. In the forward, we talk about how information flows from one part of the module to the next. And then the other thing to make a note of is that our final output here was the output from a linear layer. So this is just any value between negative infinity and infinity. What we're doing is we're doing a classification, or really a binary classification, of an outcome as being either yes, they have diabetes, or no, they don't have diabetes. So we really want a probability between 0 and 1. In other model tools like TensorFlow Keras, you might have a activation function here to handle that. In Pytorch, you normally don't do that here as part of the model. You instead just have the evidence or the logit come out as your output, and then use the loss function to handle the sigmoid part of it. So that is just one little detail that may be confusing if you're going back and forth between different frameworks. All right, now that we have the model defined, we can go ahead and instantiate an instance of the model by calling it. This is again like sklearn syntax for those familiar with that, where you're just saying, I have a model, now I want to have a particular example of this type of model that's been defined. The second thing I need is to define a criterion. Now this criterion is the loss function you're going to use. It defines what is your metric for saying whether or not the model is doing well or not. In this case, we're going to use binary cross entropy, BCE, with logit's loss. Now this connects back to what I said a moment ago, where we don't have an activation function here. We're outputting just the raw value from negative infinity to infinity, which is going to be the logit for it. And so we have to have the right loss to match with that. Now, it can be really, really confusing and problematic to get the exactly right loss function when you're trying to use Pytorch. You have a lot of functions with very similar names and descriptions that don't sound all that different. Generally speaking, the best way is to find an example of someone doing a problem like yours, where you can ignore all the details of the actual model and everything else except for what is the last thing they're outputting, and are they trying to do a categorical with multiple categories, or binary, or a regression problem. And based on that, look at the criterion they're using, and that will be the one you want for your application. Right. And the third thing we need is the optimizer. Now the optimizer is really the method of how we're going to do our gradient updates. So the gradient itself, if you're just going to follow it directly, uses stochastic gradient descent is your classic answer. Other ones like Atom, where you have a more sophisticated way of doing it, are also available, and you can just choose whatever one you like. Inside this optimization method, we do have to tell it what it is we're updating. Now, in principle, you can make very complicated models of Pytorch, where you have different layers and different pieces that are being controlled by different optimizers. In general, you don't have to worry about this. You're usually just going to use the same optimizer for everything. And so the easiest way to tell it what parameters it's allowed to update is use model.parameters, and it will find all the coefficients being defined by your model and say that this optimizer is responsible for updating all of them. And this .parameters is a method that just kind of came along for free from the Torch module up here. Otherwise, the other sort of standard parameter choices you generally want to play with are the learning rate and the momentum. Most often momentum of 0.9 is a good choice. So if we run that, we have now defined all the pieces we need in order to build a model to actually begin fitting it. So we've now gone back and forth a little bit and made some pieces. So this is a good point to go ahead and just do kernel, restart, and run all. When you're building something, especially for the first time, it's very easy to go back and forth and get something out of order because you made an update and get confused. Now, everything has run successfully. So let's go ahead and do our first bit of actual data fitting. To that end, we need to load in our data from the data loader. And now this next part of code here, the next several lines, is pretty much just a boilerplate that you're going to use again and again. There really isn't much that you're going to change. But it will take a moment to go through what all these pieces are doing. All right, in the first line, we're just looping through the data loader we have. Second line, we're just splitting the data into the X and Y pieces. Third line, optimizer.zeroGrad, all we're really doing is saying, okay, the optimizer is part of its calculations, keeps some and stores some internal variables. We need to just reset those between updates so we don't have any mistakes when we write things. Next. Now, this line here is one of the more key lines you'll actually use outside of the immediate context. And what it says is take the model we have, give it some data, and see what it predicts for the outputs. Now, this is the piece when you actually want to run the model externally. You have some data you want to plug into a model, see how it's doing. This is the line you're going to use. We also use it as part of the training process itself. But in the training process, we then take and feed it to the criterion, which will compare the results we've predicted, outputs, to the y values that are correct. Now here, remember, y, it was a value of 0 or 1, depending on whether or not the person had diabetes. Outputs, though, is instead the evidence for whether they have diabetes, and it's evaluating from negative infinity to infinity. But because we're using a criterion of BCE with logit loss, it knows how to interpret the difference between these two and make the appropriate loss calculation. After that, we do loss.backward, and this is really the key line, or one of the two key lines, that is doing all the heavy lifting under the hood for Pytorch. In the loss.backward line, it calculates the back propagation step for everything we've done. You'll notice back in the original model up here, we find the forward propagation. We told it how to glue these different layers together. We never actually had to tell it how to calculate the back propagation. It figured that out completely by itself and does it here. And then we have the optimizer.step. And what this does is simply takes all the information from the loss backward propagation and then updates the model parameters that we've patched to the optimizer appropriately. All right, now this piece of code as written here is correct. However, as you'll see, we're going to get an error when we run it. So what went wrong? Well, let's scroll down and look at the error we got. So this error is one of a common set of errors you're going to run into a lot around shapes. We see that this matrix multiplication between something called mat1 and mat2 is failing. Mat1 apparently is a 32 by 8 object, and mat2 is a 9 by 16 object. All right, so this is a little bit hard to follow in the highest level of like, why is there something that's not matching up? What went wrong? Inevitably, the error is almost always something to do with how you're defining the number of layers inside of your model itself. And if we actually scroll up here slightly, we can see we got a pretty good hint in this case of what went wrong. A little note here is that the calculation error occurred during our forward propagation step. So actually scroll up just slightly further, we can actually see it originally happened when we tried to use the model to calculate outputs, and then within that process, it happened specifically within our forward propagation. This is perhaps the most common occurrence. It's also good to note here is that if you're using a model that you didn't define, that you downloaded from somewhere, pulled from somewhere, if you see this forward method as the one that has the error, this still gives you an idea of what kind of issue is causing the problem. In this case, it's because there's something wrong with how FC1 is defined. It's not consistent with the data in some way. So, keeping in mind the error we have is 38 by 2 and 9 by 16, let's go look at our model. All right, so we see in our model, FC1 is 9 and 16. Ah, okay, that we just saw the size a moment ago, 9 by 16. When that 9 by 16 was at matrix 2 that was having an issue, was the linear transformation of values from 9 outputs to 16. Under the hood, a linear transformation or fully connected layer is just a matrix multiplication. And we have a 9 by 16 object is the coefficients or the weights within the layer. So that's where that 9 by 16 came from. The other piece is the input that came to this, so the x value. And our x, which is just our original x when we do this calculation, is actually the input from our data. Looking up here, we see he had a batch size of 32. And so a 32 by 8 object tried to multiply by a 9 by 16 object and failed. In this case, it's because there was a mistake made about the number of inputs or number of features that were in the input. If we actually go back to our very original data, we see we had a data table that had 9 columns, which is where I grabbed the 9 from. However, we didn't have 9 features because the last column was being used as our output. So when we actually grabbed the data, right here, we dropped one of the columns in terms of features for the input. So we had 8, not 9. And so we had a 32 by 8 object instead of a 9. All this is to say that the error is occurring because 32 by 8 can't be multiplied by 9 by 16. And so our model should just have an 8 here. Right? And just getting little mistakes in these numbers is by far the most common error you're going to run into. All right, so now we've gone ahead and fixed this. Let's do our kernel, restart and run all, and see what other errors come about. All right, after that runs for a moment, we will see the next error we've left for ourselves is a little bit more complicated one. This is Boolean value of a tensor with more than one value is ambiguous. This is a pretty hard to follow error. Now, this one is one of the errors that you just are not going to have a whole lot of luck kind of stepping through. We can see back up here that, okay, the error happened on the line of the loss where the criterion was taking the outputs and the y value, and then we get some internal code that doesn't look like much. If you are more experienced with computer science and these kind of debugging things, you might recognize this line is kind of specific because it's this super in here in the init is telling you that this is part of some sort of initialization of a class. If you're not, don't worry about it. This is just a specific error that does come up in Pytorch because it comes from a very common typo. And without belaboring the point too much, the issue is that criterion itself is not defined correctly. And this is because there's a mistake in the boilerplate. What we have here is the criterion is this BCE with logit loss. It's actually not just the class name itself. It has to be an instance of the class that's initialized by calling it with the parentheses the same way we call the model with parentheses. Now again, this is a very hard error to actually like debug and figure out, other than just saying, do I have a mistake in my text and going through everything line by line. I would not worry about necessarily debugging this one per se, but it is a good case of understanding that if you do have an error, a lot of times, like these pieces, you copy and paste them from somewhere, or you're trying to write them by hand from somewhere, go back and just check where you're pulling it from. In this case, I wrote all this stuff by hand. And that, in general, is not always the best way to do it. It's great for demonstration purposes, but if you know you want something, copy and paste it from a working example, and you won't run into this kind of error. All right, so let's do it in kernel and restart and run all again, and we have one more error to look at. All right, now this time, once it finishes running, the error we're going to get is another shape-related error. This one's a little more understandable, and the kind of shape error you would expect to be able to debug from the information provided itself. This one says that torch size 32 must be the same as input size 32, 1. Okay, so obviously we have something that's size 32, something that's size 32 by 1. That's not the same, so what's broken? Come and look, it's exactly the same line, even the error, the criterion. And now we don't really have as immediately obvious a way of seeing what's going on internally that's some sort of big hint. All we can really see is that, okay, during the actual call to the underlying function that uses the binary cross entropy of logits, something isn't lining up correctly. And it's throwing an error because target size doesn't equal input size. Now, if we actually want to investigate this, the way we could do it, we say, okay, criterion gets outputs and y, complaining about size, let's just look at the shape of these two pieces. Outputs.shape, run that, and y.shape. And we see, okay, this is exactly where the error is coming from. It's these two things don't have the same size. So why not? Well, if you've done work before with sklearn, you'll know that the y value you're using can be one-dimensional or two-dimensional. It works either way. That's not quite the way it's going to work here. Here, the shape of the y needs to be consistent with the shape of the output you're producing in the model. In this case, the model we're producing has a shape that is two-dimensional, has a batch size, comma, 1. Here, because there's only one value, we didn't have it already expanded to be a two-dimensional object. It's just a 1D object. So we need to expand this to be 2D as well. Now, we could fix that in theory right here and do a reshape either in between these two lines or maybe in the line itself. In general, it's best practice to change the shape as early as you can in your flow. So we're going to go ahead and go back to the original y here and do y.reshape -1, 1. And so just reshape it from a 32, one-dimensional, to a 32 by 1. Or to be completely accurate, in the y here, this is actually reshaping the original into however long our train or test set is, or the whole data set is in this case, by 1. And then when it gets split into batches, it'll be 32 by 1. All right, now we run this. We can go ahead and see that finally we have an actual running output. That's it. Provided you actually run the right button there. I misclicked and hit clear output rather than run all. All right, let me see this works, and then let's go ahead and just get rid of these for cleanliness. And run. Okay, so while all that ran, there's still one more error I'd like to touch on here, which didn't come up naturally in this case, but is a very common Pytorch error, and that is to do with data type. So, for example, let's pretend, for example, that our data for y actually was not in the form of a float, but was instead a long integer or long type. If we then ran this piece of code here, we would have gotten a runtime error like this that said result type float can't be cast into the desired output type long. And what's happening here is not going to show up when you look at the shape or look at the values themselves directly unless you're paying attention to the decimal points. But the outputs is a float value. The y values were integers, which between the answers are 0 and 1 was a perfectly reasonable way to represent it, and it could have been the way it came in. In this case, the CSV file happened to actually have the values written so that the zeros and ones got transferred to floats instead of to integers, so there wasn't an issue. But many times it will be. So if you have a value that is the wrong data type, you can, similar to the code here, recast it to the correct type. So you can say y equals y dot float, and you can use this dot float or dot long or other ones as necessary to convert data types within Pytorch. Alternatively, you could go back to the original data and fix it there as well by doing dot as type int dot as type float within pandas or within the numpy itself. And we can see if we run this that it now runs successfully. Again, wasn't exactly an issue in this specific case, but it is very common to have these sort of issues with the type of the data. And unlike NumPy, which is willing to say, oh, it's a float, it's an int, I'll go ahead and add them, I'm willing to do that automatically. Pytorch is very particular. If it sees an int and it sees a float, it will refuse to do math unless they're the same type. It wants you to explicitly fix it. It's not going to make any assumptions for you. All right, so go ahead and remove that. And we now, again, have running code, but we don't have any results. So let's see what we can do to actually get some interesting values here. Well, the run we have currently, the way it's set up is we're just running through all the data once using train loader. In reality, what you want to do is run multiple epochs, where an epoch or epoch refers to running through all of the data one time. For the moment, I'm just going to set it arbitrarily to run 10 epochs. We'll move that over. And then during this process, we're going to track how the loss is changing. So we're going to say total loss is 0 at the beginning of each epoch. It does its calculation. And then after we've done the hard work of actually updating everything, we go ahead and say the loss is going to be, or the total loss is going to be increased by the loss from that particular chunk of data, that batch. And then once everything is done, we can go ahead and print out the total loss divided by the length of the train data loader. All right. And if we do this, it will now print out the loss as it runs. There are a couple of little important details that come up here. First of all, when I did this, I had this dot item. What this dot item says is that, we track things with Pytorch, keep track of derivatives and how things are all connected. Well, we're done with that. This total loss we're calculating here doesn't need to be part of Pytorch's tracking of the math for where things came from. It can forget how it was calculated. And so dot item says grab out of a Pytorch tensor the actual value and don't worry about keeping track of where it's been, that kind of stuff. Generally speaking, this is just a very small improvement in performance that you don't have it connect back to it. However, there's a small chance, a small set of conditions under which this can be a major issue, because you can have things for more complicated flows, especially like reinforcement learning, where values are derived from intermediate results to calculate new targets, for example. And when that happens, if the derivatives are still connected, Pytorch will create some very ridiculous behavior around how those derivatives and calculate things all the way back when you do not want it to do so. So it's a good practice, even though for the most part it's just a very minor performance improvement, to use .item whenever you want to get a value out for something that is not part of the model fitting training. There also is a .numpy, which you're going to use if the thing you're returning is not a single value, but is instead a numpy array. Now, the second thing I want to point out is if we look at these values, these are the losses as we've been running through this. And if I run this cell again, I get different values. Now, there's going to be some random initialization of models that can cause some differences. But you'll notice that they start out at a lower value for loss, and it keeps going down. And every time I run it, it continues to go down. And that's because when I run this, it picks up with where it left off last time. The model was initialized back in this cell, and every time we run through this loop, we make minor adjustments to the coefficients and hopefully are improving it as we reduce the loss. If we actually want to see what happens after 10 epochs, we need to reinitialize the model and then run this to get the same result. So let's go ahead and do kernel restart and run all once again and see what the loss looks like then. All right, and if we do that, we see it starts off with a value close to 0.65 and comes down from there. Now, this 0.65 value is a pretty good one to know. It's actually 0.69 is the log base 2. And that value corresponds to a binary system where your model is only as good as a random guess. And the classes are of equal size. Now, because there is a finite amount of data here, it very quickly learns. And so even before it finishes the first iteration, it's already come down a little bit from 0.69. And it will continue to improve as it runs longer and longer, at least for the training set. And this is a good way to check if your normalization is correct. That you should start off with a log of the number of categories you have as your value here. If you're doing something that has an equal number of classes and the model is effectively untrained to begin with. Now, that said, there is a small error with the normalization here, because the way I'm doing this actual calculation here is I'm doing this per batch. And I'm not taking into account that the batch sizes are technically not all 32. Because you try to split into groups of 32, the last batch would usually be something very slightly different than that. And so you would need to re-weight it a little bit to get it just perfect. In this case, I'm going to be a little bit lazy because this won't make a meaningful difference on a large data set. And so you would often see it written like this. And technically, even this is sort of a misleading value for the loss anyway, because we're calculating the loss based on the value it had before the updates in this iteration. The actual training loss at the end of the epoch based on this model is actually going to be lower than this because it would perform better than this by the end. So it's maybe not really worth getting into the exact detail of how you want to calculate that. Just know that this is, to very, very close approximation, the actual loss that you have. If you want to do it properly, you want to do what we're going to do in a moment for the test loss with the training loss. And it's only if you really want the exact right answer. So let's now say, okay, training loss, it's improving. That's always a good sign. It means the model is actually training correctly. But we need to monitor is actually the test loss or validation loss. And to do that, we need to calculate it separately from the training loop itself. Additionally, we also, while loss is actually the best parameter for describing what's going on for the system, the human interpretability is a little bit limited there. So mostly people want to see accuracies, even if it isn't quite the right thing to be looking at. So let's figure out the accuracy on our test set is. We're going to go ahead and do that in another cell below. All right. So we're going to do this by initializing two values to 0, correct and total. And we're just going to pretty much loop through the data and see how it's going. So we are going to use this little helper here called withtorch.nograd. What this says is we're going to do some calculations using the Pytorch model here, but we promise that we don't actually care about the back propagation. Because we're just going to be looking at how this model does on the test data set, we absolutely don't need to do anything with the derivatives to update anything. So we might as well go ahead and use this torch.nograd so that the actual system can save a little bit of energy in calculations. All right. So at the beginning, this is going to look a lot like our training loop. So we're going to loop through the data, test loader, and we're going to split into X and Y. Now this time I went ahead and added enumerate here so we get look at the index as we go. It's really not important, and I'm actually not going to use it in a specific case, but I just want to emphasize that it's perfectly acceptable to have enumerate, to have I to output some intermediate value as you go, if that is going to be helpful for what you're doing. It tends to be a preference on what kind of information you print personally between the different bits. All right, so now we use outputs equals model.x to call the model on the data we're handing it. And then we need to know whether or not our values are correct. So we need to add the number of correct answers. Now this can be a little complicated, so this builds up over a couple pieces. So first, our outputs, as you remember, are going from negative infinity to infinity. So the actual prediction in this case is based upon whether or not they are above 0. If it's above 0, they are predicted to have diabetes. If it's below 0, they're predicted not to have diabetes. So this will give us, this output's greater than 0 will give us a true-false value for the prediction. Likewise, we can say whether or not y equals 1 will be true or false of whether or not they actually have diabetes. Then we simply need to know, does our prediction equal the actual ground truth? If it does, we are getting the right prediction, or we are not. So this will then give us an array-like object of true and false values. From there, we need to see, well, how many of those did we get correct? Dot sum. And lastly, we'll go ahead and do dot item, just as we did above, to get rid of the connection to the Pytorch derivatives, etc. We technically could use the dot item back at the outputs level. It doesn't really matter because we're just making sure that we're breaking the connection and not keeping that Pytorch tracking of variables all the way through all the calculation of correct. All right. Then we also need to get total, needs to be updated. And this one is simply, we need to say how many points could have been correct, and the answer is y. All right. So if those two parts, we now have correct divided by total, a calculation for the accuracy on the test set of the model at the current moment. So we can see right now the model is getting 77.9% accuracy. If we want to get the actual training loss or training accuracy, we could do this exact kind of loop with it and just calculate either the loss by summing up losses and using the criterion, or by counting the number of correct and incorrect values, or correct and total values, and calculating it using the train instead of the test set. In general, though, the test data set is the one we actually care about. Right. Now, let's go ahead and glue all this together. So let's do that by pulling out our calculation of this and putting it inside of our loop up here for the epochs. So every epoch now, we're going to do two things. We're going to calculate and some updates to the model for all of the data, and then we're going to see what the accuracy on the test set is. This would be a good moment to actually write some notes. Assuming for the moment we do want to go ahead and get the accuracy on the training set as well, we can now incorporate the same kind of logic into the training itself above. In this case, we can say that correct equals 0, total equals 0. All right, we do the main part there with our fitting, and then we can see correct plus equals, in fact we can just copy paste, make our lives a little bit easier, that, and then we have correct total again. Now obviously we're not at the end of a Jupyter Notebook cell, so we can't just write correct total here, we actually need to store the result. For that, we're going to go up to the very top and add in history test, and keep a history of our training as we go. Okay, and actually for just appearances here, let's go ahead and just move this into that. And now here we're going to go ahead and do history train.append that, and history test.append that. All right, and we'll take a quick moment to look over this, make sure we don't have any mistakes. We can let that run. And we see we did use an N right there. Okay, run that. Okay, it looks good. Now again, we need to do a restart and run all because we're not actually starting at the beginning here. So go ahead and do that. All right. All right, so as before, we're printing out the training loss as we go. But we're interested now in seeing how the history of our axes are developing. So let's go ahead and plot those. So we can do plt.plot history train and plt.plot history test. We run that. And we see the first curve will be the blue curve. In PLT is always the blue curve. And that's the accuracy of our training set. And orange will be the accuracy of our testing set. And we see they're both improving. Okay. Now from here, there's a lot of opportunity to begin playing with the model. So let's take a step back and see what we've accomplished today. So what we've shown is how to run this one model through Pytorch. Now it turns out for any feed-forward neural network, the main chunk of code here doesn't really change. You can actually take this exact thing here, as is, and use it really for any sort of binary classification system with a feed-forward neural network. If you take out the specific details of how we're calculating the accuracy itself, then this actually generalizes to really any feed-forward model at all. From here, you can do a lot of experimentation. You could go up to the model itself and change the parameters you're using. You could add more layers, change 16 to other values. You could change the learning rate, you could change the momentum, you could change the batch size, and you could see if you can find a better way to get better results for your model. The other thing that's probably more important here is actually changing the number of epochs, because as you can see in the training set we currently have, it actually is continuing to improve. So we're probably not running it for quite long enough. But you can then monitor the test accuracy to figure out what exactly the best set of parameters are for your system. So this really then starts to take us into the questions of code organization and hyperparameter optimization, which are rich topics that deserve their own time. So with that, I'm going to leave off today and leave it to you to play with the variables, see what you can do to improve upon it, and see what the limits of accuracy actually are for this particular data. Thanks for watching, and a special thanks to those whose donations help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.